Okay, well today I'm talking about co-design, which I said the other day that category theorists take the word co very seriously, and under that definition, this is not co-design, this is collaborative design. And the idea of collaborative design is you're trying to design, say, a robot, and you've decided as the designer that you need 3 teams, one to design the chassis, one to design the motor, and one to design the battery. And that the chassis is going to provide, so for each, we have a bunch of boxes. Robot itself is a box, and maybe the robot's a part of something even bigger that someone's designing. But each box, whether it's the robot, the battery, the motor, the chassis, has some number of things on the left and some number of things on the right, and these are like sometimes called functionalities. Oh, I should also mention that everything I'm talking about today is an adaptation of work by Andreas Pensi, who was here for a while and now is I think at Zurich. And he called these functionalities. So we're designing this box, E, say, and this box has functionalities which are resources provided. So this box is going to provide certain resources, and it's got requirements, which I think of as resources consumed or required. Okay, so for example, this robot here is going to require dollars to make, but in the end is going to be able to carry some weight at a certain velocity. And the chassis is going to require a supply of torque and speed and money, but is going to provide, I guess, weight. It's going to carry weight, and it's going to carry it at a velocity. The motor is going to provide torque and speed, but it's going to require, it's going to weigh something. And so the motor and the battery, are both need to be carried by the chassis. So maybe for a bigger battery, you can get more current and more voltage out of that battery pack. But you now have to carry more. So you have to find an optimal design for this. And the feedback loops are what makes it hard. So in the co-design world, someone's going to have to design each of these motors, etc., chassis, etc. We're going to zoom in and just keep designing inward how to make the battery work, the motor work best. And we want a theory that says that all those decisions can be composed together into a decision here. So we want to decide what to do. So for example, suppose I have on the outside there, I'm carrying a certain amount of weight, and I'm going at a certain velocity. Then maybe these are design possibilities. I can get this much weight at this velocity. That's pretty good. I can get even more velocity. Wait, is that the way I want to go? At a smaller weight. So the best thing is obviously this one. I get a high weight at a high velocity. But what I meant to draw was what's called a Pareto optimal front. None of these are better or worse than any other. This one has more weight but less velocity. This has more velocity but less weight. So these are called anti-chains. If you have a post set, so velocity is forming a post set. It looks like this post set is the real numbers or the positive real numbers, but it could be any post set. Any partially ordered set or pre-order could be velocity is a pre-order, and so is weight here. And so weight, velocity times weight is also a pre-order. And in the pre-order, velocity times weight, it's not a linear order anymore. So we have certain things that are neither better nor worse than certain other things. And the problem of co-design is that we want to know what optimal solutions, or Pareto optimal, meaning anything on that Pareto curve there, are possible given a given amount of money. We want some decision. We can make the decision afterwards as a manager or something, even though we have no idea, even though our model has not distinguished any better or worseness between these. So the co-design situation, well, we want to formalize this whole situation. So any questions about that? About what we're trying to do? Yeah.
Sorry, back on, you said anti-chain, what does that refer to?
An anti-chain, so in a post-set or a pre-order, P less than, an anti-chain is a subset, well, I'll call it A, I guess, in P. So here's my P is all the dots on this grid. A is the thing that's says Pareto optimal on it, with the property that, such that, for all A1, A2 in A, if A1 is less than A2, then A1 equals A2. In other words, no two different things are comparable. So these two could not be in an anti-chain together. These two could not be in an anti-chain together because one is strictly less than the other. But anything of this shape. So I guess it'll be all the monotonically decreasing curves in this kind of funny case of reals. Okay. So I'm going to start talking about what this whole thing, about how to do this. And the idea, the categorical idea, is the ProFunctors. So these are going to be feasibility relationships. Especially where V is bool. The whole thing I'm talking about today is parameterized by different V's. You can take the whole discussion, and I'm going to use two different V's. One is bool, and one is cost. But you could also take V to be the category of sets, and run this whole discussion again. And instead of asking, so in the bool case, I'm going to ask, can I get a motor that can provide this much torque and this much speed for this much weight, this much current, this much voltage, etc.? Can I? For the V of cost, it says, how much would it cost to get this much torque and this much speed given these three things? So cost would kind of be internalized in each one of these boxes instead of being sent out to the world. And set, if I used V equal to set, it would say what are the set of implementations of a torque and a speed given a weight, a current, etc. So can I, how much does it cost to, and what are the ways to are different V's. But today we'll mainly be talking about can I, is it feasible to? Okay, so the idea is that a V category, the V categories are going to be the wires. And V profunctors are going to be the boxes. And V profunctor composition is like the whole co-design problem, like designing the robot. Composition and trace and all sorts of like words that we don't necessarily know yet. But tomorrow, or is that right? Tomorrow, Brendan will talk about the rest of the setup. I'm going to get through this stuff today. He'll talk about how this is a compact closed category and how in any monoidal category, we've already seen we can draw these wiring diagrams, and those feedback loops are what are called compact closure. So tomorrow, I guess this is like feed forward. Profunctor composition is feed forward co-design, and then what's called compact closed structure equals feedback, adding feedback. And this is tomorrow. So any questions Does anyone remember what, if V is bool, what is a V category? What'd you say?
Pre-order.
Pre-order, yep. It's a pre-order. So it's got a bunch of dots, and one can be less than or equal to another. That less than or equal to is a true-false question. And the composition law says that if A is less than B and B is less than C, then A is less than C. And the identity is that A is always less than A. So in a co-design problem, I said that the V categories are going to be the wires. And so what this means is that posets, that the wires there are labeled with posets. So what poset do you, and I kind of already made that clear that the weight, or pre-orders, I always confuse those. Velocity and weight are pre-orders here. Velocity times weight is also a pre-order. So every wire in this thing, you want to have more. The pre-order structure of the less than is whether it's better to have A than B. And better means whenever I have A, I can use it if someone just asks for a B. So if I have $10 and you ask me for 5, I can use my 10 and supply you the 5 you need. So the pre-orders associated to every wire here are, we have to assume for your model that having 10 watts or 10 volts is better than 9 volts. That if, whenever someone gives you 10, that you could get 9. If you can't take a million volts, if you don't think a million volts is better than 10 volts, then you don't put a less than between 10 and a million. So you have to kind of make that decision up front of what is usable for what. So if I can carry 100 pounds, I can carry 10. You decide that up front. If that's not true, then you make a different pre-order here. So each of these wires is carrying a pre-order or a V category. So in other words, if V is bool, each one of those wires is carrying a poset. And if V is cost, each one of those wires is carrying a metric space that says, if I had 5 watts, how much would it cost, say, what's the cost of getting 4 watts? Cost 0 or cost 2 or whatever. Okay, so each wire is carrying a pre-order, and now I need to tell you what a profunctor is. So a V profunctor, and you guys, maybe I should say this first. Do you know what the opposite of a V category is? If you have a V category, what's its opposite? Its opposite, given a V category, say P less than, well, I'll call it just P. Its opposite is a V category with the same objects. So if you think of a V category or a poset, as a bunch of dots with some arrows between them, then the opposite is the same dots with the arrows backwards. P op from x to y, or P1 to P to P prime, is P from P prime to P. So if you want to know what P op is, its objects are the same as P, and its morphisms are the morphisms reversed. So you take your whole poset, just turn the arrows around, or you take your category, turn the arrows around. And now I'm finally ready to tell you what a V profunctor is. A V profunctor from one V category to another is often written with one of these slashes through it. It doesn't mean anything, it's just the name of the arrow. And I'm calling it phi for feasibility. So this will be a wire and this will be a wire, say, and this will be a box, I said there. And what is a V profunctor? It's a functor, it's a V functor. V functor P op times Q to V. So this is a regular old functor, this one's a profunctor, but they mean the same. Like this guy packages up that. So what does that mean? It means that for each, so let's unpack this. So in category theory, we often talk about unpacking things. You write this very concise definition, and then you unpack it to see, like, what does it mean in my case. So unpacking, so we can call this phi again, because it's the same data. Phi of some PQ is Q feasible? Is P feasible given Q? And the answer is a V, which is a Boolean, which is a yes, no. So is it feasible? Yes, no. Or is it feasible? Yes, at a cost of 0. Yes, at a cost of infinity. Yes, at a cost of 4. Depending on V, we're answering different types of questions, but it's still, or we're answering questions in different ways, but it's still the question of how feasible is it, or how do I do it. So we're saying that given a P and a Q, we get a yes, no, true, false. But there's also this whole op thing and non-op thing. So what's that about? That says that if P prime is less than P. So what if I said, can you give me dinner for 2 for $20? And you say, yes, that's feasible. And then I say, actually, I just need dinner for 1. Can we still do that for $20? That's always going to be feasible. If I'm asking for less requirements, or if I want to provide less stuff, I want to provide dinner for 1 instead of dinner for 2, then if I could do it with some resources for 2, I can still do it for 1. Consume, require, I don't know. So if P prime is less than P, or if Q is less than Q prime, either way, feasibility of P given Q is less than feasibility of P prime given Q prime. So as you can see, the P prime is like less on this side, so I'm going backwards here, which is why there's the op, and I'm going forwards here. If I can provide dinner for 2 for $20, I can also provide dinner for 1 for $30. Yep?
So a V-functor is a functor between 2 V categories?
Yes.
Does that mean that V is a V category here?
Yeah, good point. So here, V is what's called, in today's discussion, V is a V category. It's also, which means it's enriched in itself. So it's also what's called a quantale, which means it has all joins, and that the joins commute or distribute across the tensor. So what that means is something like, so for Booleans, you can take OR of lots of different propositions. You can OR up. You know, you have true, true, false, false, true, false, true. You can OR that all up and get true. In cost, you have 3, 5, 7, and 2. You can take the infimum of that. That's the join in cost. And we need the property that the join of the join over like some set of A and B is equal to the join over that same set of A and B. That's how you say that join distributes over or sorry, this is the tensor. Anyway, so yes, B is enriched in itself, and any quantale, this is so quantale. It's in the book, but for this class, you don't really need to. I'll just use it, and you'll see it being used. And for more details, see the book. Okay, any questions about this feasibility idea of why it's op or anything else? Yeah.
Is the P prime less than or equal to P that's in P op? Or
This is in P, which is that P is less than P prime in P op. So if you wanted to see, here's P less than P prime in P op. Here's Q less than Q prime in Q. And this is really the one I'm kind of saying I'm using. Like they're both directed in the same way if you opposite P first. And yeah. So if I opposite P first, P is less than P prime. I wrote it this way because it's easier to think about it. Or for me, or I don't know. Okay, other questions? I think actually I had on my page for you guys to discuss this with a neighbor, so maybe you can do that and see if you understand what's going on so far in terms of what we're trying to do and how we're planning to do it using V ProFunctors. The goal then is to take this whole co-design problem there and understand it in terms of compositions and feedback of ProFunctors. So see if you understand like how that's going to work, what this is all about, talk to somebody and figure out whether you each understand.
I'm not aware that we didn't go through
We didn't do V
It's in the whole website.
And it's all sort of more like, I feel like it has down, or like, but like the details of it, I think, are and I've been finding that kind of sitting down just after these lectures are very heavy, and sitting down and trying to kind of think through, like, okay, digest that. So, I guess you're great, like, I captured these ideas.
I will try to fix that.
Right.
Well, maybe you will.
Well, yeah, capture ideas.
So I think the question is,
And so you
and less required.
more than providing or
okay, so yeah, we'll just make it
Okay. Any questions? I have some questions that people have already asked that I'll soon talk about. Namely, why are there so many strings here on the left and right, and why is there only one thing here and one thing here? What's this picture have to do with it? Another question is, what exactly, how exactly is a V category a category? What does it have to do with each other? And maybe what a V functor is. Other questions? What's a profunctor? A profunctor is this. A profunctor from P to Q is a V functor from P times Q to V.
So the opter is different.
And the fact that instead of going from P to Q, you're going from a P and a Q and getting a true false. Other questions? So, yes.
So what's a V category?
What's a V category? So you may have missed some earlier classes.
Yes.
Is that true? Okay. So V categories were discussed on a certain day,
Wednesday,
and
last week, a week ago.
and now I'll say what they are again, because I think we all kind of, or I won't say it completely. Well, should I? Okay.
Pretty quick.
Of V category. Am I really doing this? V category. Oh, so V is a symmetric monoidal poset or a symmetric monoidal category. A V category consists of one, a set of objects. A V category is P, say, a set ob P of things that we're going to call the objects. Just a set, and two, for all P1 and P2 that are objects. And I'm going to draw these as dots. And for all P1, P2, an element, P1, P2, that's an element of V. So if V is Booleans, this is a yes, no. Is P1 less than or equal to P2 or not? And then the conditions are A, P of PP holds equals true. or the top element of V.
I is less than the monoidal unit. Sorry, greater than the monoidal unit.
Right. So here V is a V, a tensor, and an I. So I is less than the monoidal is that, and 2 that P, P1, P2, P2, P3 is less than in V, P, P1, P3. But the way we draw them, what's easier, that I probably just should have gone right to, is we draw a bunch of dots. And this is called the Hasse diagram for P. And here are all the objects of P. And then we draw arrows to indicate that one is less than another. And one is really less than another if there's a sequence of arrows or a path from one to the other. So here, yeah.
Sorry. Do you want to label them by elements of V?
Yeah, these are really labeled by elements of V. So in a profunctor, in a Boole profunctor, these are labeled by whether they're there or not. If they're there, then I'm saying that it's true. And if it's not there, I'm saying it's false. In a, or I'm not guessing, yeah. In a cost profunctor, in a cost category, I label them by elements of cost. Cost is 0 through infinity. And so I might say 2, 1, 4, 3, 2, 6. And so the cost of getting from here to here is 9, because I can take this route. So it's the minimal cost to get from there to there. Okay. So in a Boole profunctor, yeah. So here's an example of a Boole profunctor. You can draw a Boole profunctor in terms of what's called its collage. This is some profunctor from x of x to y. So in other words, it takes an x and a y and produces a Boolean. And over here, I've taken an x and a y and produced a cost. Okay, so what's going on here is for every element of x and element of y, I have to tell you yes or no, because that's what a profunctor is. And if I back up in x or move forward in y, yeses have to remain yeses. That's what this says. If I back up in x or move forward in y, and I was at a yes, I have to remain a yes. So the picture of the collage is you draw an arrow. It's kind of like a Hasse diagram for the whole profunctor. You draw an arrow to say that there's a yes from E to C. There's a yes from S to A. So if there's a yes from S to A, is there a yes from S to C? Yes. So now we can write this down. So here's the actual profunctor phi, or whatever I call this thing. X is north, west, east, and south. This one's A, B, C, D, and E. And is there one from north to A? Is that a yes or a no? There is no way to get from north to A because to get from one to another, I either need an arrow or I need a path. Basically, I need a path through this one, then an arrow, then a path through that one. That way, it'll be closed under backtracking here and forward tracking there. So is there one from north to A? No. False. Wait. I'll write that symbol for false and the opposite for true. Is there one from north to B? Okay, where is there one? North to C? No. D? No. E? No. Yes. From west, the only way west can get to anything is by going through east, by going through north. So this looks exactly the same. False, 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 true. East. Can east get to A? Yeah.
Why can't you go back from north to south? Because it's x up and then to A.
Okay, let's, so let me fill this out for a second. So east goes to B and C, but not A. And yes, D. And yes, E. And south goes to
Wait.
everything except for, oops.
Sorry, I don't think it goes to E.
Right. Everything except for E. Okay, so you want to know,
Wait, what?
oh, it goes to E. Sorry, south goes to E. Both
Oh,
East goes
sorry.
East goes to
Yeah, okay.
Okay.
Yeah.
So the thing that we need to check is, if I put a true somewhere in this table, and I go up in Y, I'll have a true in that table in that spot too. Alex, I think I'm answering your question right now. So if you can check anywhere in this table, find a true, and if you can go up in Y, it will remain true. Or if you go back in X, it will remain true. And the reason that works is because if there was a path from something to somewhere else, and something's back, then there's still a path from that further back thing. I just go up and then across. Yes, yeah.
So intuitively, the contravariance of x bounded input cancels out with the opposite. So there are two things that map where they cancel each other out.
I guess so, yeah.
Okay.
Yeah. It seems like there's no op here because all the arrows are going the same, like in the direction they like to go, and we're just drawing pictures and it's very intuitive, and yet somehow this one's opt. And the reason is because the thing that's being opt is, does this work? Like, sorry, the thing we're answering is, is there a path? And paths get extended by going backwards here, and paths get extended by going forwards there. The existence of a path is only helped by going backwards through this one. Yeah.
I might be missing something, but so far when we've been talking about functors, they've looked like functions. So how come we have two arrows coming out of E?
Yeah, this is a profunctor and not a functor. And a profunctor is a functor to bool and not to y. It's from x op times y to bool. And so what's happening is I'm actually taking a 20-thing diagram of this thing op and this thing forward, multiplying, getting 20 nodes, and then going to a little bool yes, no thing.
Okay.
And that's what's secretly like that's what this is looks like from that point of view.
Thanks.
Sure. Now, someone wanted to know what a functor is. Also, a functor is a kind of profunctor. A functor is a profunctor which you can draw as a collage, or this is the collage of it, such that you could draw it where every one of these dots has exactly one place to go. So here this E had two places to go. This west, although it looks like it has no places to go, does have an E. So I could have just as easily drawn another arrow like this. And that would have meant the same collage as long as like this commutes, which in bool, everything that could commute does. So putting that aside, a profunctor is a generalization of functor where you're allowed to not include everything in the domain, which someone was asking about yesterday. Like, what if I have a functor, but I don't want it to come from everything here, just some things? Well, that is still a kind of profunctor. Or I might want two things to spread out, that's still a kind of profunctor. So a profunctor is a functor if you could redraw it where every one of these source dots had exactly one place to go. Which is what you were thinking of when you said we've been drawing functors as everything here has one place to go. And I would say, yes, if the collage looks like that, then your profunctor is a generalization of, or is coming from a functor. Every functor is a kind of profunctor. Yeah?
So the way you've drawn x, if we're thinking of it as things that can be provided,
Right.
is like, if I can make an n, does that mean I can also make an s?
These are what I'm providing and these are what I need.
Right.
And so it says, I can give you an n if you give me an e. I can give you a little e. I can give you a big E if you give me a B or a C.
So the order in x, if p is less, if x1 is less than x2, right?
Then I would rather have this than this.
Right.
Yep. I'd rather have west than south. And so if I can get a west using if I can get an east using a C, then I can also get a south using a C. Which I said in the beginning, if I can get a dinner for two for $20, I can get dinner for one for $20 or for $30. Other questions? Yeah.
Does this mean that we're interpreting X as the functionality and Y as the?
Yeah, and all these guys, the left-hand side is the functionality and the right-hand side is the requirements. Other questions? Did you have a question? Yeah.
So X and Y here are V categories?
X and Y here are V categories. A V category is a diagram like this where the arrows have been labeled with elements of V. The V knows how to compose by what's called tensor, and yeah. Other questions? Let's see, I have 15 minutes, and I think I'm late. So I was going to have you work out the table for this one, but it's in the book already, so I guess. But just for example, what's the distance from C to Z? C to Z. Well, I think that's kind of odd. I think it's probably 17. 6 from C to Z.
Oh, I see. So 17.
Yeah. What about from C to Y? 17. Yeah, there's a way to get from C to Y that costs 3, 11, and 4, which I think is 18. But you could also get from C to Y by going 3, 5, 9, which is 17, which is cheaper. So the distance, if I was going to write out this table and put C's A, B, C, D over here and X, Y, Z over there, I would put for C, Y, the minimum distance. And that can be calculated with matrix multiplication, where the matrix multiplication is, well, I guess I'll talk about profunctor composition in just a second. And that involves a kind of matrix multiplication. But just the profunctor itself can be understood by writing down this guy. I should leave that to the book. Brandon kind of talked about it last time, or a couple times ago. And there's a way to figure out that the fastest distance from C to Y is 17 by multiplying matrices. So let me talk about that. Oh, before I talk about that though, I just mentioned that a profunctor is a functor is a kind of profunctor. And we know that Brennan said that a functor between Boole categories is a monotone map. So any monotone map should be a profunctor. So if I have a monotone map, for example, n times n, n is a Boole category, where the order is 5 is less than 6. And there's a map that takes two natural numbers and adds them, and that's monotonic. Because if A is less than A prime and B is less than B prime, then A plus B is less than A prime plus B prime. So that's a monotonic map, and so it should involve some kind of profunctor. And what profunctor is it? It's the profunctor that takes the dots in this grid, the n by n grid, and returns their sum, of course. And that profunctor, as I said before, will take, I guess I didn't need anywhere near this many dots. But as you can see, the arrows go up and right. And so what sort of, if this is a functionality provided and this is a resource, it's kind of like you're drawing a box with two natural numbers and you're providing two natural numbers given a natural number, and it's kind of like you're cutting the cake or whatever with, and maybe my mom would say oh, I get a tax or something, so she gets a tax. So it's just that she'll, given like 5, she'll give a 2 and a 2 and say, here you go, and she'll cut it evenly with a tax. So as long as, so the profunctor says that a point here, there's a path to a point here, if when I add the 2 coordinates, it's less than this sum. And I use that box over here when we added weights. So I told you I was designing a robot and we needed to design the chassis, the motor, and the battery, but I secretly had these 2 pluses that you might have thought, like, why are they in the picture and why didn't I talk about them? Well, they are profunctors that are just coming from monotone maps, from V-functors. And yeah, so it could be that we can carry even more weight than we say, in the same way that you can have a tax. So, yeah?
So is the formal definition of a profunctor, like?
Did I not define it formally? I did, okay, yeah. Is the formal definition what?
Or, that's like a V.
Oh, for any, whenever someone says a functor or a category or a profunctor without mentioning the V, they always mean a set category or a set profunctor or a set functor. Right. Set is a monoidal category. And yeah.
We haven't told you what monoidal categories are.
We haven't told you what monoidal categories are.
Oh,
Brendan will talk
Rich
about
over
them
one.
next time.
Okay.
Or at least that's in the book for
Yeah.
The reason I'm only talking about V being a monoidal preorder today is because that's all we've talked about so far. But I'm giving you a hint that can be extended to that. Other questions? Okay. So profunctors can be composed, and I guess that's what I'll talk about next. We need to compose profunctors because if I have a profunctor from P to Q, and a profunctor or a box design problem from Q to R, so I have some feasibility relationship there and some sizability, a feasibility relationship there. I need to compose them to get a feasibility relationship from P to R. So given a PQ, I can say that's feasible. Given a QR, I can say whether that's feasible or not. And now I want to know, given a PR, is that feasible? And so what should it be? So if I want to take phi, or phi, and compose it with psi, and then ask the question, is a PR feasible in that thing or not? You can kind of guess what it should be if you think about the semantics. Like, what does this mean? Well, it means that they found some, we can find some Q in Q, such that phi says that P is feasible given Q, and psi says that Q is feasible given R. Now where is this and taking place? It's taking place in bool. That's a Boolean feasibility, yes, no. That's a Boolean, yes, no. This is the and this is the or in bool. So I said that we needed a quantile, which means we have all these ors and they distribute. And now we're using our big or and our and to compute the composite feasibility, yeah.
Is here V considered to be commutative?
Is V considered to be what?
Commutative.
Yes, V is a symmetric monoidal preorder with joins that distribute over tensor. A quantile. So V is a quantile. And again, this is written in the book, what a quantile is and why you need it. We need it so we can write the symbol. We need that it distributes over and so that composition is associative. So what do you think the identity profunctor on P is? It's a functor from P op times P to bool, or to V. What do you think it is? The identity profunctor, every time you see a string, secretly there's an identity profunctor sitting there. So what is it? P has to decide, identity on P as a profunctor has to be able to decide, given a P and a P prime, whether to say yes or no. It could say always true. Other ideas? But that might not compose right because then, well,
P is less than P prime?
yeah, P is less than P prime. But how does P write that?
P P of P, P prime?
Yeah, P of P, P prime. And this is the one that if you check it will give you the right answer. So these are all about feasibility relations. Can I make a blah given a blah? Can I provide this given this? And P itself has a notion of whether it can provide 5 watts given 6. That was what P is. So in general, for any V category, like that category is its own profunctor, has an identity profunctor that asks, is there a way to get from here to here? What's the cost? That might be a bit too far, but you can talk to me in 5 minutes about that. So what I had to do next was to either write out the proof of associativity or, because associativity, when I do a phi, a psi, and a, what, lambda, I don't know, some other Greek letter, I'm going to have to do this twice, and the ors basically come in and interact with the ands and stuff like that. I could show you that proof, or we could just end early. Or any questions? Next time, Brendan's going to talk about feedback, which will complete this diagram, make this diagram completely understandable, like the semantics of it. It's going to say we're going to put a profunctor in each of these, and we're going to compose them whenever we see forward tracking, and we're going to put what is called this feedback or trace structure whenever we see feedback. So Brendan, next time we'll discuss what this is all about. But any questions? Yeah.
To tie back to what you were saying at the beginning about Pareto optimality.
Right. Yeah.
So you can see whether things are feasible and whether things are more than other things and whatever. But you see the Pareto optimality in the exact composition.
What Andrea? So I told you that Andrea Censi invented all this whole idea. He didn't know about Boolean profunctors. He just did all of this stuff in the way that seemed most sensible to him as an engineer. And it just turned out to be exactly Boolean profunctors. And he also made a programming language that's open sourced at, I think, Censi.science. I don't know where he got the idea to put science as that's the address. But anyway, what it does is it passes around the anti-chain, the Pareto optimal anti-chains. Instead of passing around the Boolean profunctor itself, it takes in a certain amount of dollars or whatever and produces the anti-chain of all Pareto optimal things that this one says. Pass it through and kind of like uses what's called the Kleene theorem, K-L-E-E-N-E. Uses the Kleene, I know Kleine's grandson, and he pronounces it Kleene, so I think it's Kleene as opposed to clean or cleaning. It uses the Kleene theorem to determine the anti-chain here. I don't know if I answered your question, but the point is that this Boolean relationship, if I just save the anti-chain of, like, given an input, I tell you the output anti-chain, then I can also tell you the feasibility relation by just checking if something's less than that optimal anti-chain. Is there something in this anti-chain that is less than? Other questions? Yeah.
So you said that a profunctor is a generalization of a functor, but it's also defined here in terms of a functor.
Yes.
And I guess I'm having trouble wrapping my head around that.
Yeah, that's the primordial ooze. So category theory is very fluid, in the sense that lots of things can be defined in terms of other things. So you define functor first, then you use it to define profunctor, then you realize that functors could be understood as special profunctors.
Okay.
If you need, so often we need to do things linearly just so we can kind of have a place to stand, and that's important. But often you can also start from lots of different areas, parts. And yes.
Does a V category also generalize a category?
Yes, when V is the category of sets, you get a category. You can take V to be the category of topological spaces, and you get, instead of a set of maps from one to another, one thing to another, you get a whole space of maps from one to another. When you take V to be vector spaces, you get a vector space of maps from one to another. So just like I said, V was enriched in itself, it turns out vect is enriched in itself. Given any two vector spaces, there's a whole vector space of maps. So the blank of maps is the V. In bool, when V is bool, you get a yes, no of maps. Yeah. Question?
Unless this is for after, or better for after, but where did, like, you've shown some examples with cost, but we never talked about, like, what does it mean for cost to be enriched in itself? And I'm wondering how that shows up in this stuff, if it does. The fact that this like, what is the requirement that a V profunctor be a V functor mean when the V is cost?
Good question. Maybe better for after, just 'cause I can't answer in 30 seconds. Anything else? In 30 seconds? Okay, so let's end and then come on up afterwards and happy to answer more questions.